And now we have Hiroyuki Katsura from the University of Tokyo, who is going to tell us about higher order property-directed reachability. And once again, online, please post on the Discord thread. I'm going to revive it and to mute myself.
Can you see my slide?
Can you speak?
Okay. Sorry. Okay. So, hi, I'm Hiroki Katsura from the University of Tokyo in Japan. And today I'm going to talk about higher order property-directed reachability. This is a joint work with Naoki Kobayashi and Ryosuke Sato. First of all, PDR, or property-directed reachability, is one of the most successful methods in the context of first-order program verification. However, we want to consider automated higher-order program verification, and we think automated higher-order program verification is still not satisfactory. So this situation gave rise to the following questions. What would PDR What happens if PDR is applied to the higher-order program verification? And if it's possible, then does it work effectively or not? To answer these questions, we formalize our method HOPDR for new HFLZ, which is a higher-order logic for program verification by utilizing polymorphic refinement intersection types. We also implemented a preliminary solver based on the proposed method, and we also evaluated our work with previous existing solvers. And finally, we compared our work with other methods by refining their methods in HOPDR's our style transition rules. But we don't dig into the detail of this comparison in this talk, so if you are interested, please refer to our paper. First of all, we want to talk about our motivation of this research. We want to consider automated higher-order program verification. And in fact, in recent years, various approaches to automated higher-order program verifications have been proposed, including host model checking, or refinement type inferences, or logic program verification. However, we think that they are not still satisfactory in terms of efficiency or expressiveness of the background type system. So this is the motivation for considering yet another approach like HOPDR. Then, what is new HFLZ and why we target new HFLZ when we formalize HOPDR? New HFLZ is a high-order logic with integers and greatest fixed points. And it can capture properties of higher-order functional programs very naturally and uniformly. Consider the following situation. Given a program in some language, and you are given a specification like lack of assertion failures or uncaught exceptions or whatever. And now you have to write a verifier for this program. Then if you use new HFLZ framework, then you can just reduce the program to the parity checking of new HFLZ formula, and then use the off-the-shelf new HFLZ solver to check if the original program is valid or not. And in fact, this is the similar situation in the first-order context. CHC solving or CHC satisfiability checking is utilized for verifying first-order program verification widely. And to solve satisfiability checking of CHC, PDR or spacer, which is the extended version of PDR, is utilized. So in this sense, extending PDR to higher order is reasonable. And so now we want to look at how it is applied to OCaml program verification now. This program, sum function, takes an integer x and calculates the summation from 1 to x, and then finally passes the result to the continuation function k. And in the main function, it takes an integer n non-deterministically and passes that integer to the sum function, and finally checks if the result r is greater than or equal to n. Does this OCaml program never fails, or in other words, does this assertion never fails? This is an instance of safety property problem of functional programs. And this kind of problem is reduced to the following new HFLZ variety checking problem by the reduction of Kobayashi and others in a sound and complete manner. And actually, we don't dig into the detail of new HFLZ formula syntax, but basically, new HFLZ formula is comprised of a top-level formula like this and fixed-point equation like this. And this function, sum function, is actually a higher-order recursive function, and it is reduced to the following higher-order predicate that is defined by greatest fixed point. And if you look at the body of the program and higher-order predicate, then you may notice that the cross-correspondence between them. And from this observation, you may understand this reduction does not lose any information. So that's why we think this is like this UHFLZ can capture properties of higher-order programs. And then the main function is reduced to the following top-level formula of new HFLZ. And now, what we want to do here is to solve this variety checking problem automatically and efficiently. And this is what our work is tries to do. Then, before we talk about how to solve this variety checking problem by utilizing HOPDR, we want to talk about PDR, which is the first order setting. PDR takes a transition system like this, input init states and bud states and step function, and checks if the bud state is reachable or not from initial state in finite steps. So if there is a counterexample from initial state to bud states, then we can say it's reachable. But if you want to prove unreachability of the problem, then you have to infinitely expand the post condition due to the existence of integer arithmetics. So to saturate in finite steps, we have to invent some good inductive invariant which satisfies these two conditions. And first condition says inductive invariant is invariant to the post condition, and inductive invariant also does not violate the state T condition. So if you can find this kind of state sets, then we can say the original program is valid. But how do we do it is the problem. To do so, PDR, in the PDR, we rephrase the original program to like this. Instead of thinking that expanding initial state finite and infinite times, we consider from both sides. Then in PDR, we over-approximate and under-approximate of these state sets by like this. And actually, this CI represents the under-approximation of expanding bud states for k minus I times, and Ri represents the over-approximation of reachable sets in I steps from initial states. And by repeatedly refining these configurations, PDR hopes to find an inductive invariant in finite steps. And in the context of first-order PDR, CI, which is a counterexample, is represented as the model of the background theory, and Ri is represented as the first-order formula. But now we want to consider higher-order setting, and then how to handle higher-order predicates in these states. This is the problem. And our key idea for HOPDR is to use refinement types for expressing approximations. So in the higher order setting, we consider refinement types as the over-approximation of reachable sets, and CI, which is a recursion-free formula, as the counterexample, so that we can handle higher order predicate in the counterexample naturally. And in fact, these types and formulas are considered to be extended version of state sets. So if you express these configurations in this way, then you can naturally extend PDR setting to the higher order case. So to explain this higher order property directed reachability, we want to talk about our refinement type system. Our refinement type system is, in fact, an extension of refinement type system proposed by Cathcart, Ban, and others. In terms of that, our refinement type system contains polymorphic types and intersection types. And intuitively, our refinement types give over-approximation of formulas. And in this sense, we think higher order, this kind of refinement. Can you hear me? Okay. This kind of refinement type is considered to be higher order extension of state sets. And this is the syntax for refinement type. And this guy is the type of phi such that theta implies phi, right? So the formula x is greater than 0 has the following refinement types like this. And this is the syntax for the predicate that takes an integer. And this, importantly, can you hear me? Okay. Then, so let's talk about this refinement type for the predicate that takes an integer. In our setting, tau can depend on x, which is this integer variable. So we can write this kind of refinement type for this formula. And then thirdly, this is the syntax for higher order predicate. And importantly, in our type system, we can write intersection type at the position of argument. Okay. Finally, this is the syntax for polymorphic type. Then if you ignore this higher order part, then we can say that this refinement type is equivalent to the approximation of the PDL setting, original PDL setting. Because if you translate these reachable sets in the original PDL can be reduced to the following refinement type. Then by utilizing this refinement type system, we formalize higher order property directed reachability. First of all, now instead of thinking of transition system, unreachability problem of transition system, we consider variety checking of New-TFLZ formula, where it is represented as top level formula phi and fixed point equation. For example, this is an example of New-TFLZ formula. And now the goal of HOPDL is the type environment gamma, like this, such that these two conditions hold. And recall that the first order setting of PDL, this condition can be considered as the higher order extension of this one, which is the first condition for inductive invariant, and this one is the higher order extension of this condition. And so this condition says that for each type assignment in the type environment gamma, we can assign that type to the body of the type fixed point equation under the assumption of type environment gamma. And probably this is we can understand analogy to the typing of recursive function in functional program literature. And secondly, this condition says gamma is strong enough to prove the validity of the top level formula. So if you can find this type of environment, then we can say the original problem is valid. And so then to find this kind of type of environment, HOPDL tries to refine and rewrite configuration of the form like this, as we did in PDL. So, and this is the high order extended version. So, gamma I represents the higher order over approximation of fixed point with I time unfolding of fixed points. And secondly, counterexample sequence CI represents the under approximation of counterexample with I time unfolding of fixed point. Then we want to find this type of environment gamma by rewriting these configurations using these transition rules. And this rule is actually a higher order extension of the original GPD proposed by Hoder and Biona. And you don't have to understand the detail of this rule itself, but basically each rule says that given a configuration like this, then these assumptions are satisfied, then we can obtain another refined version of configuration. Okay. Then we want to see how these rules are applied to a running example. So we want to consider this example. This is an example of UHF-FEZ formula, and this one top-level formula says m is greater than 1 implies Fm, where Fm is defined as the fixed point equation, and so if it's defined as the greatest fixed point that satisfies this equation holds. This instance is actually valid because if you consider replacing fx with x is greater than 0, then from the top-level formula, we obtain this formula, which is trivially true. And also from the fixed point equation, we obtain this formula. This is also true. So in this sense, we can say m is greater than 0 is a candidate for an inductive invariant. But now, how to find this m is greater than 0 automatically is the issue for HOPDL. So let's see how the HOPDL finds this kind of inductive invariant by applying the transition rules and rewriting configuration one by one. First of all, HOPDL starts with init rule. This introduces the strongest type environment to the sequence of approximation. And unfortunately, strongest type environment is not invariant. So the HOPDL thinks that we have to collect more information from fixed point equation. So we unfold once the fixed point by utilizing unfold rule. And by utilizing unfold rule, we introduce the weakest type environment to the approximation sequence. Then this weakest type environment is not strong enough to prove the validity of the top-level formula. So now we obtain counterexample to this type environment, counterexample formula to this type environment. And then we want to check if this counterexample is spurious or not. And in fact, you don't have to understand this derivation itself, but this counterexample, it can be refuted by utilizing the previous type environment, top gamma. And by finding this type environment, by using procedure that we introduced, we can apply conflict rule like this. And by utilizing this type environment, we can say this counterexample phi can be derived. So we introduce this type environment to the sequence of the approximation, and then now the sequence of approximation is refined. But unfortunately, this gamma 1 is still not an inductive invariant. So we continue to unfold fixed point again, and we obtain another candidate. And at this time, we have more information than before. And if the interpolation solver is smart enough, then we obtain this type environment by utilizing this conflict rule. And fortunately, this is an inductive invariant, so we can conclude by utilizing this type environment, this original problem is valid. This is how HOPDL finds an inductive invariant by repeatedly rewriting configurations. But how about invalid case? Now, we modify this part here, so now this instance is invalid because if you unfold this fixed point twice, then you obtain 0 not equal to 0, which is obviously false. And so for this instance, actually the initial procedure for disproving this instance is same as the previous valid case up to this part. But for this part, actually after the second candidate, this formula, it could not be proved under the type environment gamma 1, unlike the valid case. So we obtain another counterexample by expanding the fixed point of the counterexample like this, and by applying decide rule. Then we obtain another counterexample by expanding the counterexample again, and now the length of the counterexample sequence is equal to the length of the type environment, so we can say this instance is invalid. Okay, so this is how HOPDL repeatedly rewrites the configurations and obtain counterexample or inductive invariant. And so far we explained our procedure by utilizing a first order formula, but actually for the simplicity problem, but actually in our paper there is running example for higher order formulas. And also probably you may wonder how to find a good type environment, gamma prime at conflict inference. And actually this is another important issue for HOPDL, and it is explained also in our paper. Also, there are some properties that are required for refinement type system to make the HOPDL works effectively, and there are also other technical details for making the whole procedure work efficiently. So if you're interested, please check our paper for the detail. Finally, we want to talk about the experimental result. So far, we talk about how HOPDL is formalized, and based on this formalization, we implemented preliminary solver based on the proposed approach. And we also take a benchmark set from safety property problem of higher order function programs. And we conducted an experiment like this. And unfortunately, PDL-HFL or HOPDL itself does not outperform our other existing solvers. But we think there are some promising results. First of all, PDL-HFL could solve problems that RESTful could not, where RESTful is the state-of-the-art new HFLZ solver. And another thing is that PDL-HFL tends to solve unsafe instances faster than before previous methods. And finally, virtually combined solver, PDL-HFL plus RESTful is the best solver among these higher order program verification methods. And so from these experimental results, we think this solver is complementary to the previous method. Finally, we want to talk about our related work. First of all, there are some existing UHFLZ solvers, like based on constraint Horn clauses solving or predicate abstraction and SIGA. But we think our solver is complementary to their solver. And another thing probably you may wonder is that HOPDL is the higher order extension of PDL or not. And from the comparison we conducted in the paper, we confirmed that PDL for linear H2HC is obtained by a special case of HOPDL. So in this sense, our procedure, HOPDL, is the higher order extension of PDL. And finally, our procedure is also applicable to full HFLZ validity checking as a building block of their solver. And full HFLZ validity checker can handle arbitrary temporal properties. So in that sense, this uniform approach can obtain more wider properties can be handled in this framework. So this is HOPDL, and finally we want to conclude our talk. We formalized HOPDL on top of polymorphic refinement type intersection types, and we formalized HOPDL for new HFLZ validity checking. And we implemented a preliminary solver based on the proposed method and evaluated our work with the benchmarks and compared our work with previous methods, and we consider that our solver is complementary to their solvers. Finally, we compared our work with other higher order program verification methods so that we can see how different it is. And so if you're interested in this part, then you can refer to our paper. That's it. Thank you for listening. And yeah, I'm happy to take some questions.
Could the third speaker please come forward to the podium while you can line up for questions? Once again, please tell us your name and affiliation and hit the mic. You can also ask your questions on the Discord thread. And while there, do you have a question? Sorry.
The speaker is remote.
Ah, yes, okay, thank you. You have a question? Ah, okay. Then I do have a question. So if you could back to, 2 or 3 slides before, please.
3 slides before. Okay. This one?
Yes, thank you. So you mean that PDR-HFL could solve problems that RETHFL could not? What kind of problems that? Yes, what kind of problems?
Basically, these problems are like, firstly, unsafe instances are not, RESTful is not good at solving unsafe instances. Mm-hmm. And secondly, RESTful is not complete in terms of the background type system. And there are some instances that cannot be handled in the background, in the framework of RESTful. But our system contains homomorphic types and intersection types, and in this sense, expressiveness is greater than their method. Okay. And in such, such instances can be solved our solver, but their solver cannot solve such.
Okay. Thank you. Oops, if you can stay on this slide, maybe. Let me think. Do you have one idea why PDR-HFL alone performs worse than the other servers that you showed here?
Basically, the type system itself is a bit difficult compared with other solvers. Okay. This is one reason. And another reason is probably other methods finally reduces the problem to the background, like well-implemented solver like CHE solving or other host model checking methods. And their solvers are good at finding fixed points, but we have to handle such kind of fixed point solving in this framework. So in this sense, we have to implement more to efficiently find fixed points in this framework. So this is the second reason probably.
Okay, thank you. Any further questions? Let me see if, is there any question on Discord? Let me see. No, any further questions? I think if there are no further questions, then let's thank the speaker again. Thank you again.